Are there any questions on the lecture or the material seen so far? There's a couple of things I would like to go through, but I'm very happy to go off on tangents if people have additional questions.
Maybe a quick one.
Sure.
Okay. Why is the distance between space-time maximally, how do you say it? The proper time is maximal.
Yes.
Why?
There's two answers to that. One is the answer that, the way that I gave in week 3 of this course is that I said, well, the fact that all space-times, when you look very close by, is and you make things extremely temporal and extremely local, then all space-time look approximately Minkowskian.
Mm-hmm.
And in Minkowski space-time, things go in a straight line from point A to point B.
Yeah.
Right? That's Newton's first law. That's by almost by That's by definition on what a inertial frame is. That things follow Newton's first law. So they go from one point to the next in a straight line. But that also means that the amount of time that it takes for that thing to go from A to B is the shortest amount of time.
Yeah.
Now, that means if you have this curved space-time, you have this very local, small temporal patch where things take the path of shortest space, shortest distance, shortest proper time, then that means at the moment that it's gone on to the next small patch of Minkowski space-time, it will there take the path of shortest proper time. And if you continue that for over all of the curved space-time, and in every patch it takes you the shortest amount of proper time, then the total amount of proper time must be minimized.
Yeah.
That was the way that I did it in the lecture. So my argument that I gave in week 3 was just really based on the idea that the fact that you can split up a space-time into small patches of Minkowski space, in each of which by definition Newton's first law holds, that's enough. And then we got to the point where, okay, if the total amount of proper time must be minimized, and you know that in a curved space-time proper time is given by this expression, you have to minimize this, then all of a sudden you are back in what in special relativity we did by Euler-Lagrange equations. Now, if you minimize this integration, what I'm just really asking is, what should x mu as a function of tau be such that this integral does become indeed the smallest proper time? You can use the Euler-Lagrange equations to solve that. And then the solution to this...
Hello.
Hello. We were just talking about you. In a good way. So we're happy that you're here. That if you then indeed minimize this as a mathematical exercise, then you find your Euler-Lagrange equation. Then you find your geodesic equation. That derivation, by the way, is I now last night posted online. So if you want to, so I hope you understand this part.
No, the thing is, in the textbook it says it's maximal.
Oh.
Is it? Really?
Yeah. Isn't it
They
just
do.
extreme?
It's
Extremized. This thing, minimize or maximize it, will result in the same geodesic equation.
Okay.
Because the only thing you have to do to get this to be either maximum or minimum is say that its derivative is equal to 0, and that holds for both maxima and minima.
Okay.
I have no idea why the book would say maximum, probably because they don't care, because the resulting expression, the geodesic equation, is true either if it is maximized or minimized. Now, I'm just guessing what the reasoning behind this particular way of phrasing it in the book is. I have a suspicion, and that is the book doesn't say why this is true, it just states it as a separate law of nature. Right? The book never says you can splice, well, it does say that you can splice up space-time in small patches of Minkowski, but it doesn't say, and therefore the total amount of proper time is minimized. So what I think happens is, because they omitted that step, and the outcome is going to be the same for maximize and minimize anyway, that for some reason there was no point in of the two choosing the minimum over the maximum. That's what I think happened.
It gave an example of the twin paradox, and then it said one of them is going to go in a what line, right?
Yes.
And then it said if you swap to that person's coordinates, it will always be that person that does that. Wait.
Yeah, but wait a minute. No, that's a different story.
Okay.
Yes, because what I now did was I took a curved spacetime and I made it into small patches, and in every patch the proper time should be minimized. Okay. In the twin paradox, you're not switching to different. You are switching to different coordinate planes, so both of them are Minkowski. So that means you can go to another coordinate system, but that will not make any statement on whether it's minimized or maximized.
Okay. If it's just like extrema, then sure.
Oh yeah. No, again, the mathematics will give you the same result. Now again, I'm just guessing what went on in the minds of the people who Jim Hartle wrote that book. I'm guessing that because he never did explain that it should be minimal, and the answer is going to be the same anyway. For some reason, he chose maximum because it doesn't matter for the answer anyway.
Okay.
That's what I'm guessing. There's no physics in the minimum versus the maximum.
Sure.
Now I said there's two ways that you can come to this conclusion about the minimization. There's a second way. In fact, that's how the Weinberg, the classical textbook, does it. They do it in a different way. What they say is, if you go to a different coordinate system, then your Newton's first law changes by a certain amount. If you go to a different coordinate system, then you know that what used to be a coordinate now changes to a somewhat different coordinate, right? That's what you do if you go to a different coordinate system. And then he derives how this what the path is in the new coordinate system that it will look like, and then he finds his Udesque equation, which to me is very visual. You just say, well, I know that things follow Newton's first law in this coordinate system. I go to another coordinate system, then it probably will not follow a straight line anymore because you're not in an inertia system anymore. Then he just derives from Newton's first law, then this equation holds, then he finds the Udesque equation, and only then does he say, by the way, this is also, this equation also tells you that the proper time should be minimized. So he concludes the proper time as a conclusion, whereas I took it as a starting point. I mean, it's all the same thing. It's just what is your starting point, what is your A, and what is your B. So that is the second answer why the proper time should be minimized. If you go to a different coordinate system, you'll get a different equation for how things move. That's a Udesque equation, and then you can mathematically show that it corresponds to the shortest proper time. So
Right.
that's how Weinberg does it.
I have another question.
Yes.
In the singularity of the smart symmetric, they say that it's because the coordinates are not well defined there.
Yes, that's correct.
I don't understand why that is true
Okay.
there.
In fact, let's take that one in to do the whole the Ricci tensor, the Ricci flat exercise 1. Right. Because Rodrigo was saying that he went through, calculated for the 3 different space-times, the 3 metric tensors, he calculated the Christopher's, and then calculated the Ricci tensor. It becomes these huge amounts of expressions. That's all true. Can go a lot faster, and that is by remembering, and then your answer will be part of this fuller explanation. There we go. So this is the exercise on the Ricci flatness, and the question was, explain or find out whether Minkowski spacetime is Ricci flat, Schwarzschild spacetime is Ricci flat, and whether a Robertson-Walker time is spacetime is Minkowski flat. And yes, so that means of these 3, which of these 3 have this as a result? For every alpha and beta, right, there's 10 components in Ricci tensor. Which of these 3 spacetimes is such that all these 10 numbers are 0? And yes, one way would be to take the definition of the Ricci tensor and actually calculate the whole damn thing. And that takes an enormous amount of time. It's not difficult, by the way, it just takes an amount of time. Just calculate Christopher's, put those into the Ricci tensor because that is defined in terms of derivatives of Christopher's, and work the whole thing out, and it gives you enormous amounts of things. And then check whether the total outcome is 0. Correct. It takes time. Now, people who want to try this, and not by hand, but they do want to try it in this way by actually working out the Ricci tensor, the cosmology lecture notes that I uploaded. I wrote in chapter B a Mathematica program that does this for you. So if you just copy paste into Mathematica, you just press a button and it will calculate the Ricci tensor for you. You don't have to do it yourself. But there's a much quicker way of doing this. No Mathematica, not doing it by hand, just by doing it as follows. We showed last Tuesday that the Einstein field equation, we'll call this one Tuesday, if it is 0, then automatically that means that this must be 0, and that that must be 0, that they're 0 apiece. That was one of the exercises that we did on Tuesday. But it also means that Ritchie flat, this thing being equal to 0, is just equivalent to saying it must be a universe in which there is no energy and no momentum. And that all of a sudden makes life very difficult, because a Minkowski spacetime is a spacetime, by definition, in which there is no energy and momentum. So a Minkowski spacetime is Ritchie flat. It so happens that Minkowski spacetime is extremely easy to calculate the Ritchies, because the whole tensor is just ones and minus ones, so the derivative is all 0, so that immediately gives you 0. But it's nice to do it by this way. If your spacetime does not contain matter or energy, it must be Ritchie flat. Okay, so Robertson-Walker, is that Ritchie flat by this argument? So
But Robertson-Walker is just the expanding. There's like the circle, the sphere one and the flat one and everything, right?
Yes, but is it Ritchie flat?
Yes.
The flat one is.
Is there a matter of energy in that universe?
It
Yes.
depends. You can put matter and energy.
No, it's because of the cosmological principle. So there is, because it's homogeneous.
Yes, but an empty universe is also homogeneous, I suppose.
That's
So it is, of course, yes. But generally speaking, you're allowed to put in any pressure and density of that Friedman gas, right? So that means, aside from that very peculiar case of universe when it literally has no matter or energy in there, generally speaking, the Robertson-Walker metrics are the result of universes that have some rho density and some p pressure. So it is not Ritchie flat. Yes, you can also do it by taking the Robertson-Walker metric, put it in here, and work through all the derivatives and everything. You will find the same conclusion. It is not equal to 0.
But on Tuesday you said that even if there is matter and energy, then T mu nu can still be equal to 0.
Okay, that brings us to our third option, Schwarzschild.
Okay, but how do you know immediately that that's not the case with Robertson-Walker?
I will tell you after we've done the Schwarzschild. I hope that will answer your question for the Robertson-Walker as well. Because the Schwarzschild spacetime doesn't contain matter and energy, and/or energy. Schwarzschild is the curvature of spacetime due to the presence of a spherically symmetric mass distribution.
Yeah, but I think you said that for this kind of for Schwarzschild like spacetime, TMV is equal to 0, like the tensor.
Yes, but why? I mean, how can I, on the one hand, say you get this Schwarzschild spacetime because there is a mass in the middle, and at the same time say, by the way, there's no mass there?
Because there are different solutions of the equation.
Oh, that is true. The Einstein field equation can give you. We did talk about that.
Mm-hmm.
I told you indeed in week 4 that if you have the Einstein field equation and you set it equal to 0, then one of the solutions indeed is Schwarzschild. So that answers the question, by the way. That means apparently, mathematically speaking, Schwarzschild solution can be the solution to an empty spacetime. So that makes it Ritchie flat. That is the answer. Schwarzschild is Ritchie flat. But it does come with a strange physical paradox, right? Because yes, mathematically you can show that it is a solution to the Schwarzschild, to the Einstein field equations in the absence of matter or energy. Yet we constantly talk about this black hole in the middle that certainly has some mass. In fact, the whole Schwarzschild solution has a value m in there. So, I mean, I'm sort of contradicting myself, it seems. So, now what? So, is there, on the one hand, mathematics tells you it's okay. It's a solution to the vacuum Einstein field equation, so therefore must be Ritchie flat. On the other hand, they say there is a mass in the middle, so something is going on here. And I think Rick will tell you the answer in a moment. Yeah, can somebody ask Rick? Okay, Rick has been harassing me for weeks that he wants to give one lecture on black holes. So please ask him that question. He's now about to come in. Hi.
Hello.
Hello.
I'm the guest lecturer.
Okay. These students might have a question for you.
Okay, then start with the question, please. I'll just start off with the talk I wanted to give. You all probably heard there's a public transportation strike this Tuesday, which means that some of you may have troubles coming to the exam or not. The rule as it is stands right now is that we are not allowed to cause any negative consequences whatsoever for you if you are unable to make it because of the transport issues, as you received in the email. So I just came in here to clarify what the situation is and to ask if there are any expected issues right now for any of you, and if you have any questions regarding that.
No, I think it's fine.
I think we're okay, yeah.
Goodbye.
No questions, Gideon?
I know,
Okay, that's
I know
great.
the answers, but
We were seeing why the sword shield is one of the solution, is a Ricci flight space basically. So why is it one of the solutions to zero to the Einstein field equation?
Good question. I don't know anything about general relativity.
that's fine. I will take over.
Yeah, thank you,
Yeah.
Gideon. All right, have a nice day and good luck preparing
Yes.
the exam.
Thanks.
Thank you.
Oh, Gideon, is iedereen hier?
Nee, er zijn twee mensen die er niet zijn.
Kun je me zo laten weten?
Ja, dat ga ik doen.
Dank
It is true. Already in period 2 or so, he will say, "Oh, I read something about black holes. I really want to give one of the tutorials." I said, "Well, you're free to do so." And then, he came back regularly to it. He said, "Yeah, remember that that I could give one of the tutorials? I said, if you want."
Is he a physicist?
No, not at all. But he did see a documentary on black holes.
Then he's an
Oh, okay.
I don't know. He is. I don't know exactly what his background is. It's not. It's not in science. Anyway.
I was thinking that
Yes.
maybe it's zero because there is no exchange of energy. You have a spherically symmetric mass. It's not rotating, so there is no rotational energy. There is no other object around that it can interact with.
Okay, but sure. But the T mu that you have on this side is not just about exchange of energy. It's also just about the mere presence of it. In fact, the T mu that you have here, right, itself can be written as a matrix if you want.
Yeah.
The 0, 0 part is the amount of rest mass, even mass that's not moving about.
All right.
So your argument will be fine to argue that all this other stuff may be zero, but that part you cannot get rid of. No, but it is a good question, right? I mean, something is up here. Now, if you go to the Schwarzschild metric, what happens if you go to r equals 0 in that expression? You might recall the expression for the Schwarzschild space-time metric.
It blows up.
It blows up.
Infinity.
Yeah, I mean, one of the terms in there is 1 minus 2m over r. 1 minus 2m over r minus 1 or something like that. But certainly this one will go to infinity at r is 0. Now, that means that this expression is fine. I mean, there's nothing actually physically going to infinity in the center. It just means that whatever goes on there is not well described by this particular mathematical form of your space-time. So the question is not so much is there something physically going on there, it just means that whatever goes on there, this particular form of your space-time metric might not be the best one.
So it's only defined well outside of 2m
Yes.
where there's no mass.
Exactly. That's the thing.
Can you repeat that again, please?
Yeah, absolutely. The Schwarzschild space-time is only mathematically well defined. But this means it doesn't blow up because it doesn't go into infinity or something like that. At any point outside r is 0.
Wait, is it just r is 0, not r is 2m?
No, there's
Not
also
the
something happening there.
Event horizon.
Yes, there's also something happening there. Let me get back to that in a second. But the R0, that part is clear. Yes, at R0, the mathematics breaks down. What happens physically is a separate question, but mathematically already it breaks down. And that simply means that this space-time, the way that we write it down in this particular choice of the metric, doesn't work at R is 0. But that means you're not allowed to use it at R is 0. You're only allowed to use it outside of R is 0. Now, outside of R is 0 is where there is no matter or energy.
No, but if the black hole has a size,
It
r is
doesn't.
0 is just the center.
But it doesn't.
It's a singularity.
It's a singularity.
But,
But-
the event horizon has a size.
That's true.
But can the Schwarzschild then also work for just massive objects? I didn't know it was just like excluded to black holes.
No, you can also apply to any spherically symmetric mass distribution. So it also applies to the Earth if you take away that it's also rotating.
Yeah.
But mathematically speaking, this is something that we call Birkhoff's theorem. This is a mathematical fact of general relativity. That any spherically symmetric mass distribution can always be written as if there is exactly one mass in the exact center of that space-time. That is Birkhoff's theorem. Birkhoff's theorem says a little bit more than that. It doesn't just say you can pretend as if all the spherically smeared out mass distribution, as long as it's spherical, can be seen in the center of the space-time. The second thing that Birkhoff's theorem says is it's always given by the Schwarzschild space-time. So even if you have a spherically distributed, so a non-singularity, just a finite amount of mass distributed over finite amount of space, then still mathematically it's not a right way to describe it.
So if
You have no choice, sorry, just one sentence in between. You have no choice but to describe it by the Schwarzschild metric. This is Birkhoff's theorem. And this thing breaks down at R is 0.
And also r equals 2m, no?
Yes, there's a subtlety that I will get to in a second. Just get to the R0 part, let's have that everything completely understood. So, you have no choice if your mass is spherically distributed to write it as a Schwarzschild spacetime. This is the Birkhoff's theorem. And unfortunately, the thing has the mathematical aspect that at R is 0 it blows up and therefore cannot be used at R is 0. Outside of R is 0, you can see it as a vacuum.
Okay. So even at r is some value less than the radius of the object, it's as though there is no matter.
Exactly. Yes. Again, this is the Birkhoff's theorem part.
But that's a physical property of space-time. It behaves as though there is no matter in the area
Sure.
around r equals 0.
Okay. Yeah, that's true.
That's weird.
No. That's you might find it weird, but it's already true in Newtonian physics. If you would replace the mass of the spherical the mass distribution of the Earth.
The force is only coming from the center. That's
Yes,
true.
exactly. So even in Newtonian physics, in fact, Newton even already wrote it in his Principia. He already at some point concludes that the gravitational field of the Earth is exactly the same as if you would have taken the 6 times 10 to the power 24 kilograms and had put it in exactly in the center. So this is just the extension. Birkhoff's theorem is the extension of that Newtonian theorem. It still holds true in general relativity. Now that means for all practical purposes, and I really do mean that in all practical purposes, for every calculation that you want to do on how things move, either in general relativity or Newtonian physics, you can pretend as if all the mass is in the center. In general relativity, that means it must be given by the Schwarzschild spacetime. But the Schwarzschild spacetime has a mathematical property that it blows up at R is 0, so therefore you're not allowed to use it at R is 0. There's physics there, it's just you cannot describe it by this particular expression. Conclusion, yes, it is Ricci flat because you only apply it on any point in space-time except at this length. So that gives us a nice overview of things, yes, because Minkowski's space, the three options that I gave you, Minkowski's space-time is Ricci flat, Robertson-Walker is not Ricci flat, and Schwarzschild is sort of Ricci flat, I mean, as long as you don't look at the exact center. So that's the answer to that question.
And
Then there's the 2n thing.
and Robertson-Walker is not Ricci flat just because there is mass and energy.
Yes, we get the Robertson-Walker metric by assuming that whatever is making the space-time curve is distributed as a perfect gas.
Okay. And
It has a rho and a p.
and an empty universe is just one of the options.
Yes, that's only one of them. Be sure. I mean, if you would take the Robertson-Walker metric and you would replace the energy distribution, energy density, and the pressure in that by exact zeros,
Yeah.
yes, then in that particular case, your Robertson-Walker is
Okay,
indeed.
but the general one is.
The general isn't. Yes. Okay. So yes, you could have also come by these conclusions by writing down the Christoffels and do the whole mathematics of this thing, but we can get there much faster. Okay, so that solves this. Fine, good. Oh, and then there's the 2m thing, by the way. Because things also blow up in Schwarzschild by 2m. It has nothing to do with the Ricci flatness, by the way. That matter is not solved. The 2m thing is what is called a coordinate singularity. And by coordinate singularity we mean, yes, the mathematics blows up at 2m, but that's only because we've chosen the coordinates such that they blow up at 2m. That's different from a singularity that is really there. No matter how you're going to transform to what other coordinate systems you want to go, there are singularities that will simply not go away by any coordinate transformation. The 2m one is just a mathematical consequence of the coordinates in which we decided to write our Schwarzschild spacetime.
Then why is 2m physically significant?
Because it does agree with time slowing down to an extreme, and it does agree with the extreme spaghettification part. So physically something happens there, but nothing goes to literal infinity. So one way to find that out is, well, if you can find any coordinate system, coordinate transformation that brings your Schwarzschild spacetime, your Schwarzschild metric into a different form, but in the new coordinate system there's no infinities at 2m, then you have shown that apparently the infinity that you encountered in these coordinates is just a consequence of coordinates. You know what is a very good way of pointing out the difference between a coordinate singularity and a real singularity? Let's go to Euclidean space. Forget about space-time, just look Euclidean space x, y, and z. X, y, z. Is there any difference between point A and point B as far as the space-time is concerned?
Nope.
There is not. Right. Sure, there is something about A that we happen to have chosen our coordinate system in there, but there's no physics going on there. No other physics than in point B. But if we now decide, you know what? Let's write all of this in terms of spherical coordinates. So you get your r, theta, phi coordinates. Now that expression will have something that blows up at r is 0. Right? If you write your r, your x is a function of r's and cosines and thetas and everything, then r0 has all kinds of weird properties. The inverse, for instance, will blow up at that point. Now again, nothing physical happens there, but by us having gone to a spherical coordinate system, we have introduced mathematically a singularity, even though physically nothing's going on. So that's a coordinate singularity. The 2m is a coordinate singularity, it has nothing to do with the physics. The one at the center is a true singularity, and this is why we have to exclude that from our Ricci flatness question. And the 2m we don't have to worry about. In the inside cover of the Hartle book, our main textbook, you can actually find the Schwarzschild coordinate in different, the Schwarzschild sign in different coordinates where the 2m has disappeared. Called Eddington-Finkelstein coordinates. In case if you want to look down. Same physics, same space-time, just coordinate systems such that the 2m coordinate singularity has.
So you just have to write the coordinates that you are using in Euclidean space, in the Euclidean space, and then if at some point the coordinates go to infinity, then that's a problem of the coordinates that you chose.
Yes.
Okay. All right.
Yes. And that sometimes, leads to some ambiguity sometimes. If somebody presents you with a space-time or a metric tensor of a space-time, you see some singularities, you have to find out whether these are true ones or coordinate ones. So how much of what you find in your mathematics is the result of your coordinates and how much is the result of actual physics going on there? And Einstein had the same issue when he first derived his expressions for gravitational waves. He didn't know at first whether the gravitational wave that came out was the result of his having chosen coordinates in such a way, or whether there was a real effect going on there. And for a long time he was convinced that it was just the consequence of his coordinates. There's no new physics going on there. It's just he chose the coordinates such that it made it look as if there was a wave. And then only later he found out that this is an actual physical effect.
Did he find out? Didn't he die before?
No, he found it out.
Oh.
Yes. No, yeah, he found it out himself already in I don't know, 2018 or something like that. So he was still around to find that he was correct all along. Okay, so any more questions? If not, then I propose that we solve that issue that we started a couple of days ago, where we were struggling a little bit on how can we make this coordinate transformation work. You recall this? That we had take one step back. We find it in if you take your Ricci flat Minkowski spacetime plus gravitational wave, then you found that the gravitational wave should obey this equation. You remember this, right? And then this V was some complicated expression. I even know what it is, I think. I think it's gamma H gamma alpha minus 1/2 alpha H gamma gamma. I think this was the V. That was it, yeah. So this is just the algebra. You take your Ricci tensor, you put in your background space-time Minkowski plus gravitational wave. You only stick to first order in your gravitational wave, so all H squares you just ignore from that moment on. Then this is the equation that the Einstein field equation ends up with. And we had a problem with this. It's mathematically completely fine. It's a little bit too difficult to work with. At the very least, it's a coupled differential equation. For every alpha and beta, you need the other alphas and betas to solve them. So you have 10 equations to solve, but they're coupled. That sucks. And the second sucky part was, if only these were gone, you just got back Lambertian equals 0, and we know what the solution is. And this is the question that we then were discussing. Can we go to a coordinate system? You change our coordinates in such a way that these two can be cancelled. In order to do that, this was the exercise we were attempting to do a couple of days ago. We had to show that if you go to another coordinate system, your H alpha beta turns into a new H alpha beta in new coordinates, which is equal to the old coordinates minus do you remember this? And our coordinate transformation is this, yeah? X goes to x plus psi.
Yeah.
I called it S last time. What is it? The Sydney coordinates or something like that. We can maybe we can just call it psi now. That's the original name of these things. And once this is true, we know that this H alpha beta will be replaced by this thing. You get two additional terms. Those two additional terms you can use to cancel these two, and you're fine. The question was how to prove this. And last time that we were looking at this, we got close, but we didn't quite get there. We got close enough. How to do it is the question now.
Good question.
Yeah.
But how do we know that the derivatives of psi will cancel the derivatives of v?
Because you can choose.
Because you can choose them however you want. So you can choose them in such a way that they will cancel this. I mean, if you replace this thing by that thing, you get some terms with chi, some terms with v's, but because you're free to choose your psi, the mathematical question is, can you choose psi such that these are cancelled?
Okay.
And the complete freedom of choosing your psi says yes, you can.
But then you just choose psi equals v.
No, not exactly, because you still have Lambertian that operates on these two. So these have 3 derivatives, and these have only 1. So you have to do a little bit of more thinking. But it becomes highly plausible that it can be done, right? In the fact that you could use your psi in any way that you want. That's, by the way, that's not a full triviality. Just the fact that you can choose any psi does not necessarily mean that you can cancel any term. But in this case you can. Now, let's do it once and for all. If you have your metric tensor and you want to transform it into another metric tensor by doing this coordinate transformation, I'm going to use green. So, do you remember the general metric transformation rule? Or the tensor transformation rule? You have a double covariant tensor.
We need a double derivative
Yeah.
with respect to the prime interval.
Yes.
And the prime are gonna be in the denominator, right?
Yes. So you would
With
get,
alpha and beta.
yes, thank you. That's exactly right. So this is just the definition of a tensor applied twice because you have two indices to play with. Now this step we had done a couple of days ago. We know what this will give us. Maybe it's good to write it out one more time. Let's take the derivative of x mu. But x mu is given by
Prime minus.
yeah, this is a prime. So that will give us x mu, x prime mu minus psi mu. And this was this mind-blowing step of a couple of days ago.
Yeah.
That you can use this to write these x's in terms of x primes. That's good because now we know how to take derivatives. That's the first factor. The second factor is exactly the same, of course, just with different names for the indices. X prime mu minus xi mu, and there's mu. Okay. You remember how the derivatives went? Derivative of this thing? We had a discussion.
So it went with the connected delta,
Yes.
alpha mu.
Okay. And then this
Derivative of
is.
psi.
Yeah, I'm going to abbreviate derivatives now by just one single del and a prime. Prime alpha psi mu. That's this. Same thing here. Kronecker delta
Beta
mu
mu.
beta. And here it is d prime beta psi v. Alright, so there's this. Remember that a couple of days ago we were in a sucky situation because, damn it, these are derivatives with respect to the primed coordinates. And what we want to show is that they are derivatives with respect to the unprimed coordinates. And then people started sighing very deeply, including myself, because that means that we also have to transform these using the tensor transformation rule. But I thought, no, we can do a little bit faster. There's a quicker trick to do this. I'll show you more. Let's first write out this product here. This really is a product. This is a contraction. This is a product. You will get alpha. I'm just writing out what I'm seeing. This is wrong. Okay, it's this, and another one. I get the feeling I'm doing something wrong here. Where did I get this from? This should be an alpha.
Or beta.
Yeah.
Oh, this is this one, right? This one going with
Ah, yeah,
that
right,
one.
right.
Yes. Okay, good. Then this one goes with that one. That's a nu, that's a beta. That gives you an alpha primed psi this, g mu nu. We talked about this. We're going to drop the h squares one because they're very small. Okay. Here's where we were last time. And then we have to do some more thinking. Oh, by the way, this is simple, yeah, this part. This gives you alpha beta. So really you have a conclusion here. We see that if you coordinate transform your metric tensor, you get back your original metric tensor plus extra stuff. So that conclusion we have.
How is that alpha beta?
Because this contraction over mu with this one tells you that alpha must itself be mu.
Yeah.
So you just replace this mu by alpha. And by the same argument, this mu is replaced with beta.
Oh, just the first term is alpha beta.
Yes. No, yeah, no, that's just the first term. There's stuff coming still. No. Of course.
Why do we neglect the final part of this? Because the psi thing is very small?
Yes. So that means that last term will have psi, small psi, and another small psi that's small times small is very small.
And we assume that psi is small because...
Oh, no, that's a choice. You don't have to. When we did this coordinate transformation from here to there, you can do any coordinate transformation.
Oh, okay.
Psi could be as big as you want, and as different and as strange as you want, but for our purposes, it suffices to take a small psi. Now, I'll I've done this little act before 2 days ago. Gravitational wave comes by, this is the x coordinate frame, and I decide, you know what, I'm going to go to slightly different. Slightly means xi is small. So I'm not going to jump into a rocket that itself is going to somersault, boost itself through the universe. That will be a big psi. No, gravitational wave comes by and I'm just slightly going to wiggle compared to my original coordinate frame. That's the smallness of the xi. So I'm really just doing a little bit of this maybe. No somersaults, no rockets. That's the smallness of xi. Now here's where we were last time, and we were thinking about how can we make this thing look ultimately like, where's it, like this thing. No, excuse me, like this one. Right? I mean, they're sort of close. There's a beta derivative, there's a beta there, there's a xi, there's a xi. It's so close, but it's just not there yet.
Yeah.
There's some stuff missing, unfortunately. Look, there's a prime here, there's no prime there, so we have to get rid of prime. That's one thing. And secondly, this nu is up, and here the indices are down, so we have to do stuff. Stuff has to be done. Well, we can get rid of the Kroneckers here, because this contraction with this one just means that this is alpha. And here, this nu must be beta. Okay, this is closer still, no more Kroneckers. So close. So close. What are we missing? Just drop the prime and we have to take this thing down. Then we should be good.
Is it another contraction that we're missing then?
No.
Or is it just a subtlety that we missed?
Last time there was a subtlety that we didn't take into account. Now, there's two things that have to be done. We have to drop the primes in some way, and we have to get the indices of the xi's to go down. Otherwise, we'll never end up with the expression that we're looking for. Now, how do you get the indices to go down in the first place? How do you do this generally?
There's a contraction with the metric.
Yes, but look at this. There is a contraction with the metric tensor.
So it becomes.
So
Yeah, be careful. Oh, be careful. We have the ingredient here, the thing that will make this nu go down. And then it really looks like this, right? Because now all of a sudden this will become an alpha downstairs. That is almost this thing. But be careful. This thing is outside of the differentiation.
yes.
So you cannot just freely just put it inside the differentiation. If you want to get this psi to have its index lowered, then this thing must operate on the psi within the derivative. And you cannot just take any function and put it inside the derivative. That will cost you something.
But you can add terms, no?
Yeah, to compensate for that.
To compensate,
Yes.
and then to create the product, the contracted, let's say that the derivative product or the product rule.
Yeah, sure. Yes, that can be done. That's true. So yeah, what we can do is just take them inside, but the product rule then says no. You have to subtract a term because the product rule would have given you one, right? I mean, if you take this one in, then this derivative will then be on two terms or two factors, and it's much easier to write this down than to the verbal system. If you take this inside and pretend that it's the same thing as it is now, then you will be wrong, because this derivative will now also operate on this thing. That means the product will give you an extra term, and you manually have to subtract that term. That will be your suggestion.
Yes.
Yes, we can do that, but I have a quicker argument. And that's with small machines. Because do you remember that we also introduced a certain amount of smallness to the metric tensor? We had Minkowski plus gravitational wave. Yes. And the gravitational wave we said was very small. So this thing really is Minkowski plus gravitational wave, h, but h again was small. But there was already a smallness due to psi. Right? There's two smallnesses here. One of them has to do with how much have you transformed your coordinate system, that's psi. And there's a smallness in how much have you changed your metric tensor, that is psi. That is h. But do you see that if this thing is small, then the gravitational wave part of this will make it ridiculously small? You multiply two smallnesses.
Yeah.
So that means if we decide we're going to stick to first order in smallness, we might as well ignore the gravitational wave part here.
And the Minkowski tensor is constant.
It's constant, so that you can now bring inside. So, by agreement that we're going to only stick to first order in smallness, we're going to drop the product of the smallness of the quarter transformation and the smallness of the gravitational wave. And because the resulting thing, therefore, is only Minkowski, you can bring it inside.
Cool.
Oh, alright.
And now we can do the contraction. Now we can bring it down. Can I just remind people one more time how lucky we are that we're not doing this for a Schwarzschild spacetime? Because even if in Schwarzschild spacetime we had done this trick that we're only going to restrict to first order in smallness, then still we wouldn't have been able to take it inside because the Schwarzschild without the gravitation wave itself was not constant. Life is very much more difficult in non-Minkowski spacetime. Hey, but now we can lower these things. Let's do it right here, right now. This becomes an alpha. This becomes an alpha. I'm just going to drop these. This then becomes xi beta. And now we're really close to this. It's just that we have the wrong type of derivative. Here's the derivative with respect to the original coordinates, and here's the derivative with respect to the new coordinates. And yeah, so close, but we have to find a way to drop the primes. Some argument that we can say, you know what, let's forget about the primes. If we can only get rid of these primes, then we have proven our case.
Maybe the coordinate transformation
What about it?
that we used because there is a relation with the unprimed frame.
We can certainly do that. I mean, this thing itself is a tensor. So that means that this thing itself follows the tensor transformation rule. So yeah, we could do that. We can turn the primed ones into the unprimed ones because this thing is itself as a tensor, so follows the transformation of a tensor. We could do that, yes. Now, I propose not to go through that exercise because we can already manually see what will happen, or mentally. Not manually. Do you see that?
We'll end up with more primes.
Well, we don't.
No?
No.
The beta term?
Yes, but we're going to write this thing in terms of primes. Sure, we get more primes. Okay, point taken. You get two terms here, right? Because x mu, again, is written in terms of x primed and xi. So this derivative itself contains two terms. One of them, again, will contain xi. Even if you don't write it out completely, you will see that this will give you two terms. One of them will be xi dependent. What order of smallness are we going to stick to? I'm going to throw away every double xi that we're going to see. There is already a xi here. And this transformation rule will introduce another xi. Forget about it. It's mathematically there, but if you stick to small xi, you can throw it out. And that means you only have to take into account the first term. And the first term, I'm not surprised, is just the derivative without the prime. So yet again, the first order in smallness will save us. It means that these can be dropped. This is the play again that we played. We're going to stick to the first order in smallness all throughout. So that's what I'm doing consistently. And then you get this. Man, okay, and then finally we are where we wanted to go. Namely, the metric tensor will turn into a new metric tensor. This metric tensor will go to this metric tensor, which is the same as the old metric tensor plus two additional terms. again, as long as we stick to first order in smallness. Oh. Right, this is our final conclusion for now. Green box. But wait a minute, we have to make a statement about how H transforms. I now have a statement about how eta transforms. Can somebody fill in the last step? I have a G transformation rule, we're looking for the H transformation. Easy.
Well, it's Minkowski plus H, right?
Yes.
So the Minkowskis cancel out, I guess.
Exactly. This was Minkowski plus H. Here's Minkowski plus H. The Minkowskis drop out left and right. There you go. And then you get this rule. In retrospect, it's not that hard, right? Okay, now let's have an oxygen break. Beautiful conclusion is now, we really have now seen that due to this transformation rule, if you go to a slightly different coordinate system, you end up with extra terms here. Use those extra terms, these two, to cancel these ones, and then you end up with just the wave equation equals 0. And then you get your gravitational wave.
So we're going to do the cancelling after the break.
No, I'm not going to do it explicitly.
You just have to believe either you can.
Yeah, but do you have difficulty believing that? Not because it's me, but because of the rich mathematical freedom that you have.
I believe it, I just don't know how you would do it.
Okay. At the moment that you would apply this Lambertian to the new terms that you get, that means this gets a Lambertian, this gets a Lambertian, and then the question is, Lambertian times this derivative, can you make it equal to this thing? Is there a psi such that if you take its derivative and an additional Lambertian, it gives you this?
That's like 3 derivatives.
Yes, but one of them cancels out because this beta and this beta can be crossed away against each other. So what you get, this is really then your question, does the Lambertian of this thing, or is there a solution to the question, Lambertian of this thing equals V alpha? If you can find a psi that makes that work, then that psi exists and therefore it can be done. In fact, I can immediately give you the answer, now I think about it. So, in order to have a psi that will cancel these things, your psi has itself to obey alpha equals V alpha. If that is the case, well, with the minus, because they have to cancel each other. If that is the case, then it works. Electrodynamics. Do you remember that we have actually solved an equation like this? It's a Laplace equation.
Yeah.
Yes.
Yeah.
Oh, yeah.
And the solution to this thing, we found, generally exists. You don't even have to do the integral, but we went through the integral.
Yeah.
This thing is given, alpha, by minus, well the minus cancels out, 1 over 4 pi, this thing V alpha of retarded time minus sweeping coordinate x minus x primes
Yeah.
d3x. So as long as this integration exists, doesn't blow up, then your psi exists and therefore the transformation can be done. So by the way, this is your integral. I mean, this is the city transformation, right? This is the one that brings you to a coordinate frame where things become easy.
Yeah.
So here's your integral.
That's the gauge.
That's the gauge. If we transform slightly to a coordinate system where the psi's are defined in our offending v's in this way, how would I move from my original coordinate system? Well, by this amount. Then these things drop, and then gravitational wave obeys the wave equation. And only mathematical purists will then ask, oh, but wait a minute, maybe the thing diverges. Yes, maybe it does. Maybe it does.
But it doesn't.
It depends on what your v's are.
We don't talk about that.
All right. So I think all the mathematical gaps have now been completely closed. Good. Good. We have gravitational waves, and I will have coffee.
Gideon, one
Yes.
question. It's just to clarify. The Schwarzschild, we said that the energy stress tensor
Yes.
is 0, even in Schwarzschild metric, because the surroundings do not contain matter energy.
Yes.
Yeah, the place you are in, it doesn't contain any energy.
The place that you are in, do you mean the observer himself?
Yes, for the well, let's say the surroundings.
Okay, the surroundings.
Of the
Okay,
mass.
that's correct, yes.
Okay, so that's why the Sitter universe is not Ricci flat. It's because everything is filled with this dark energy.
Yes,
Alright, okay.
that's it.
Is there any way the tensor could be zero while there's still matter and energy?
Yes.
In
So,
which situation?
I would have to think hard for an example. No, I don't know. Wait a minute. I have to think a little bit longer about this, but I think the answer is actually no.
Because we never learned how to construct that tensor, the T tensor.
That is true.
Okay.
But you don't need it to make this argument.
Yeah, I know. I just don't know what those tensors would look like.
Yes, the energy momentum tensor.
Yeah.
Well, we can be very quick about it. It's 4x4.
Yeah.
This part contains the energy density, whatever it is. This part, the rest of the diagonal, contains not pressure. This is the momentum. And the off-diagonal ones contain the angular momentum. And
Where's the
because
pressure?
it's symmetric, the other part is the same. It's also angular momentum.
But how do you find the pressure? Do you relate it through like the energy
This
density?
is not pressure.
Momentum.
This is momentum. Happens to be the same symbol. It's a
Oh,
different.
but it doesn't have a pressure.
Well, it depends on your system. I mean, if you have one single particle in this universe, it will not have a pressure. Pressure
but
is
because
a
we-
macroscopic quantity.
But because we assume the universe to be like a homogeneous fluid, I guess.
Whoa, wait. Hold on. What I write down now is not just for the Friedman gas, the homogeneous fluid. This is the energy momentum tensor in every situation.
Okay.
Yes. In the specific situation where you have a Friedman gas, yes, there will be a pressure in here somewhere. Just to be clear, this is the general expression. In the general expression, this P does not stand for pressure, it just stands for momentum. And the off-diagonal stands for angular momentum. Now, we've never quite needed it, because the only one calculation that we've done was given a Schwarzschild space, or excuse me, given a space-time metric, how does things work and move, etc. Now let's work a little bit with this right now. That's one of the other exercises on the exercise sheet. How will life look at the moment that you do a gravitational wave in the presence of matter? The conclusion that we had now, that this resulted in this in our very particular coordinate system. This is enough to bring you to the conclusion that you get a gravitational wave, goes with the speed of light, and it doesn't change shape. Okay, why? Because this thing, alpha beta, the mathematics of this differential equation tells you any function will do as long as it has this way of the dimensional space and time. Do you feel that it's useful just for a couple of minutes to go through why this particular dependence on space and time indeed means that the thing will not change shape and will go with the speed of light? Is it useful? We did the electrodynamics, but maybe we can just
Yeah,
quick.
we can.
Yeah, let's just do this. Here's a gravitational wave. Okay. This is the amount of H alpha betas. And this is the shape. And let's draw it along the time axis. Okay. Alright. Let's focus on one of these points here. Right, this has a particular shape. Where does the shape come from? We will get to talk about that in a moment. We'll introduce matter to the situation. Suppose that you focus on this point in your gravitational wave shapiness. And suppose that it corresponds to some number here. I have no idea what the number is. Some small number, because it has to be smaller than 1. Yeah? That was the whole idea. Gravitational wave should be small compared to the Minkowski. So let's make it 10 to the power minus 17. 3.14 times 10 to the power minus 17. This particular point. Good. Now, suppose I'm interested in what this point of the whole shapiness will do when I wait 1 second, I want to know where this point will end up. Suppose that is my question. That's another way of saying, what should happen to the argument if I'm interested in what this point does? That's maybe not the best way to phrase my question. Let me try one more time. My outcome for this point is 3.14 times 10 to the power minus 17. Okay? Now, I want to know at a different moment in time where the gravitation wave has this height. So this is at one particular moment in time, one particular moment in space, position in space. I'm going to wait 1 second and I want to see where this particular height has ended up. If I want the same number to come out, because I'm interested in this part of the gravitational wave form, I have to make sure that the argument of the gravitational wave itself has not changed. If I want the same outcome, 3.14 10 to the power minus 17, the argument is not allowed to have changed. Agreed? But we are looking 1 second later. So this number has increased with 1 second, but in order for the argument to stay the same so that the outcome is the same, the R must have compensated. How much must the R have compensated? Well, if you made t 1 second higher, then R must have become t times c smaller in order to compensate. Bigger, excuse me, bigger to compensate. Agreed? 1 second more here, but I want this whole argument to have to be the same number still. Then this number must have gotten bigger as well. How much bigger? T times c.
What is R exactly?
The location of this particular point, position in space. But if you wait 1 second, this has become bigger, but this whole thing must have stayed the same number, then this must have gotten bigger. How much bigger? Well, c times that 1 second. So that means that this point, 1 second later, is a particular amount of R further along. It has traveled an amount of c in that 1 second. So this point travels with the speed of light through space. So that explains why this particular point travels with the speed of light just based on the fact that the argument is t minus r. T minus r over c, by the way, if you put the c back in. Now do the same argument for every single of this point of the shapiness, and all of them in 1 second have moved by the same amount. Then 1 second later, the exact same shape is just a particular position further on. The shape has not changed. Every single of these points will have moved by the same amount, so the total shape has stayed the same. So, all in all, this equation, that we've painstakingly proved is true, leads to the fact that gravitational waves do not change shape and go with the speed of light. There you go. By the way, we had the same argument in electrodynamics when we solved the Lambertian equation, the wave equation equals to 0. For electromagnetic waves, same argument, same conclusion. Now, let's introduce mass. We can play the exact same game, and we're going to find almost the same conclusion. Now, this is part of the exercise that I wrote for you. We can do it right here, right now. Here is the Einstein equation, but this time there is a certain amount of mass and energy and momentum around. So this is an absence of mass and energy, this is in presence of mass and energy. Now, how about this thing? What is this guy's expression? If we assume again that we have a Minkowski space-time plus a little bit gravitational wave on top, what would this thing become?
Zero.
Not zero.
If it doesn't make Ritchie flat.
Yes, okay, sure. No. Wait. This was 0. We proved that this is 0 because the whole right-hand side of the equation is 0. A couple of days ago we had, if this is 0, then it means Ritchie tensor is 0. Now this is not 0, so we cannot conclude the Ritchie tensor is 0. So it's not going to be 0 per se, But it's still going to be this expression. The derivation of this expression did not hinge on the idea that the outcome should be 0. Right? If you just take your Christoffel symbols for your Minkowski plus perturbation and you calculate its Ricci tensor, and you do this particular coordinate transformation that we did before the break that we proved, you will still end up with this expression. Agreed? It's just not 0 anymore, but it's still this
It's
expression.
gonna be equal
Yes.
to something to 8p TMV, I guess.
It will be related to it, yes. But
No.
this is what this equation will do for you. You don't have to put it in by hand. My argument here is this expression in terms of h mu nu has not changed. That's still the same. All the steps that we took to get this thing into this are still the same. It's just not 0 anymore.
So
But this being equal to that is still true. Let's put it in right now. This thing is Lambertian of this unknown gravitation wave. Agreed so far? Alright, now we have this part. In a Ricci flat spacetime, we proved this a couple of days ago, this was by itself 0.
Mhm.
Now it isn't anymore. So, yeah, we have to do something with this. It should be easy.
you can replace G by H plus Minkowski.
You can. Let's do it right now. Good. And the Riemann scalar, can we do something with that? The answer is yes.
Replace it with G times the tensor.
Yes, because if you recall, the Riemann scalar is itself a contraction of the metric tensor with the Ricci tensor. So this thing, excuse me,
That's the
this is this, and this thing is G.
upright.
Let's not call it mu nu because it's already been taken. Oh,
No,
I don't know why I
beta.
went to alpha beta. It is mu nu. I write everything in mu nu now. All right, alpha beta are alpha beta.
Mhm.
That's by definition what that thing means. 8 pi t mu nu. I think that's correct. By the way, I'm a little bit sloppy because this is 1/2 here. I dropped the 1/2 because it was going to set it equal to 0, but it is 1/2. So there's a 1/2 here, minus 1/2, and then there is a nothing here yet. Question: what happens to this thing?
This is minus 1/2 the Laplacian H alpha beta.
Yes, the Laplacian, but yes.
What did I say?
Laplacian.
Use
Oh,
Laplacian.
yeah.
Laplacian is only the spatial part squared. Yeah, I mean, there we go. It's again this thing, right? So, in retrospect, things are so easy, but well, there's a G here. Maybe we should write it again as Minkowski plus perturbation.
Yeah.
So that will become.
What is the inverse G?
Yeah. What I'm writing down now is not exactly correct, but it will not matter for our argument. I'm pretending as if the inverse metric, that if I know that the original metric is something plus something, that the inverse metric is
Is
the
the
inverse
inverse.
plus the inverse. That is not true.
Inverse of the sum is some of the inverses.
Yeah, no, it's the sum of the inverse of the sum is not the sum of the inverses. Okay, so what I write down now is not correct. There's a mathematical trick for that, a mathematical rule. We're not going to need it unless you really want to know it. I will write it down for you, but we're going to get rid of this in a moment for completely different reasons. So this is not entirely correct. Will not matter for our argument. Okay, and then there's the R alpha beta, and yes, that thing itself is this thing. Now you get a plus here and a minus and a 4. You get another box. And then it is alpha beta equals 8 pi t mu nu. Look at this being beautiful. There's just too many H's in there now.
Some of them can be neglected, no? Because they are very, very small.
Yeah, everywhere where we are going to have 2 H's, We're going to ignore one of them. So that
The
means that
second part.
these will drop out. Just again by the smallness of h. This is why I said it doesn't really matter what the exact inverse is. You're going to drop out anyway. Good, good, good. Then, just cleaning up a little bit. Square, I get h mu nu plus 1/4.
But the fact that you kind of incorrectly wrote the inverse, even when you cancel h, the h is still there.
Yes,
No.
that part is true.
That part is right.
That part is right.
Why
By the way,
are
you
you-
could have also already done it here that you said, you know what, because there is already an h in this thing,
Yeah.
we might as well replace this by the Minkowski,
Mm.
Okay, yeah.
and then the inverse was obvious, yes.
Why are we dropping the Minkowski times the h? I can understand dropping the h square, but why are we dropping the Minkowski
Yeah.
times the h?
This h and that h will drop out.
Yeah, but like-
Yes, but this h and that h will also drop out.
You're timesing all of those two brackets by h again.
All this stuff,
Oh yeah.
Wait.
all this stuff before this h, all this stuff
Mhm.
will consist of some Minkowski part and some h stuff.
Yes.
But that h stuff in all of this already cancels against the other
true.
h.
Sorry.
So of all this stuff, you only have to take into account the Minkowski
Okay.
parts.
Yeah.
And then you are here. Looks complicated, right? But does it though? See if you agree with this. Minus 1/2. Lambertian. One big bracket. H mu nu minus 1/2. Agree with this? We went from here to there.
So
Yeah.
you just took out the Lambertian.
Yeah, to just took out the Lambertian. And yeah, you know what? This Lambertian doesn't care about these constant Minkowskis anyway, right? So you can just pull them through. Now, why would you do this? Why would you write it this way? Well, this thing, this strange combination of your gravitational wave that you're looking for,
It's like your new age.
it's like a new H. Not new age, it's H. And again, if you talk about, you know, curved space-times and energies, and it does sound new agey. This is a new H, called H bar, not to be confused with Jaco's H bar. If only there were two, because then it would just be one and the third will be 0. It's just a new notation for this particular version. So that means we are now have finally found this equation. Now I hope you will all internally rejoicing right now, because you know, let's put a minus 16 pi t mu nu on this side, because this is an equation that should be well known to you, right? If not from electrodynamics, then from someplace else. It says Lambertian of a thing is equal to a source. We solved this equation in
Yeah, it's the Poisson equation.
it's the Poisson equation. It's not the Poisson, sorry, it's the Laplace
Sorry, it
equation.
resembles.
Laplace.
Yeah, exactly.
Yes. The Poisson is just with the spatial derivative, so this has a temporal derivative as well. It's the Laplace equation. We know the solution to this one. It's well known in physics, mathematics. In electrodynamics, for the people who are not there, we actually solved the equation. We mathematically solved it. If you have not seen that, don't worry about it. You're just going to be given the answer right here, or right now. It's a somewhat crappy expression, but it is a solved expression. Here's the beautiful news. If somebody tells you an energy and a momentum to colliding black holes, you know this expression? then in the expression, the solution to this one I will write down in a moment, the general mathematical solution, you will get immediately your h bar. And if you have your h bar, you can calculate back what your original gravitational wave was. There you go, there's your gravitational wave as a result of this source. And you can do this for any source, because the solution I'm going to write down is true for all sources. And that determines the shape of your gravitational wave. So, what do we have here? How gravitational waves are produced. Somebody tells you the thing that makes gravitational waves. You solve this equation by this general expression I'm going to write down. You know what the shape is, how it depends on the source. Then the gravitational wave floats into space, detaches itself from the source, and then this one takes over. And that shape that we were talking about before, that will retain itself and move at the speed of light through the universe. And this is how gravitational wave research is done. People measure this thing, h or h bar, and then hope to calculate back what the sources have looked like.
So this is how it's produced, and that is how
Yes.
it propagates.
Yes, that's exactly right. Yes. Let me write down the expression. Do people remember this maybe from either electrodynamics or vibrations or waves or what have you?
No.
Do you remember having seen it, even if you don't remember the full expression?
Yeah.
Yes.
Okay. And Jan, you didn't follow electrodynamics, but maybe you've seen it in some different course. This one.
So an integral.
Yeah, not in that form. I can remember.
Okay.
It's an integral of the source over R.
And retarded time.
Yes, yes, it's the retarded time thingy. So let me just write it down in its generality.
Mm-hmm.
Again, this equation is extremely ubiquitous in physics. You will find it in many places. So, if you have some unknown function that depends on space and time, and its Lambertian is equal to some source, something that produces this f, this is the Laplace equation, then the solution f is given by the following. Why? Well, you might want to look at one of the recordings of the lecture in electrodynamics where I proved this. Not important for you, I'll just give you the solution. You take minus 1 over 4 pi. For the people in the know, that's something with the delta function. We proved this in week 1 of electrodynamics. It was this rule that had something with the 4 pi. You integrate. What do you integrate? You integrate the source, this thing. You integrate over all of space. Not over time, just all over space. That's what I mean by the prime. I do not mean some other guy's coordinate system. I just mean the thing of which you integrate.
Mm-hmm.
But you don't integrate it over time. You integrate it over something that's called retarded time. Here's the solution. Looks complicated. Oh, and then this retarded time. The R in there stands for t minus x primed over c. That's the definition of the R.
Flashbacks from this equation.
Yeah, you've seen this
Is
before.
the what is the x prime there? Like in another reference frame?
No, it isn't. That's a little bit sloppy. Well, not sloppy. It's just at some point you run out of symbols to write things in. Okay, so let me paint you a picture. Here's something. Here's a coordinate frame. Here's a source, something that makes something. This is what I mean by S, right? This could be, for instance, something that makes a gravitation wave. That is this stuff. You, as in the observer, are standing at some position x. That's this x.
Mm-hmm.
Then each of the points in the source will give you a little bit of solution. This one will give you a slightly different solution than this one because they're different distance. Maybe the source is a little bit different there. So what do? You take each and every single point in your source. That thing is called x prime. You calculate for each and every single one of these x prime points how it contributes to what you see. But you do this for every single point in your source. That's what the integral means. So this integration means look at all the points in the source, that gives you a little bit of contribution, and sum all these contributions together. Very case in point, all of you are giving me a little bit of gravitational attraction. Suppose that this is the center of the coordinate system, the corner of the room. My position, where I'm going to calculate your gravitational effect, not waves, just gravitational pooling, for instance, Newtonian. I take where I am, that's x. From my point, I'm going to sweep across all of you. This is x primed. There's you. You give me a little bit of gravitational attraction. That's x primed. I calculate how much gravitational attraction you give me. I remember that number. Then I sweep along. That's x primed where he is now. Calculate his gravitational attraction. Go through all the masses that give me up until I've had all masses. The full source I've integrated over. That's what the integration does. It sweeps over all points. It gives a little bit of contribution, and it then gives back the sum of these as the outcome. So I remember what each of your contribution is, and then I sum everything together. That's what the integral does. Makes physical sense, right?
Yeah. That the final magnitude, right?
Yes.
That's what you get. Yeah.
Of course, that's what the integral does. It just adds up small contributions. The reason that there is a TR, that we call the retarded time, is because if I'm looking right now what I'm feeling from you, I have to take into account that whatever you are giving me took time to get there.
Traveling time.
And this is, oh wait, there's a mistake here. This is this. Sorry. If I want to know your contribution to me at my now amount of time, I have to see how much you were giving me a couple of seconds ago and how much time it took for that signal to reach me. So I take your position and my position, divide by how fast it has come towards me, that's this part, and I subtract it from when I am looking. So this is really a little bit back in time.
Yeah.
This is when I am looking. This is how far away you are from me. So this is when you send out your influence towards me. So that gives you that expression. So physically it makes all the sense in the world. Proving this, taking this and putting it back in, mathematically showing that it's true, that takes one tutorial session or so. Anyway, we don't have to worry too much about this. But I call this the sweeping x prime because it sweeps over all the contributions. Now, this takes a little bit of time to do the integral maybe. We're not going to worry about that. The upshot here is, if you are given something that might produce gravitational waves, colliding black holes, maybe two neutron stars that orbit each other, whatever you want, somebody jumping up and down, you know your T mu nu, you take this equation, this integral, you solve it. Might be difficult, but in principle it's solvable. You get back h mu nu, and from h mu nu, via this step, you calculate your original h mu nu, right? This h mu nu bar, that's not the one you want h mu nu, and then you have what the gravitational wave will look like due to that source. Now, and then, yes, then it detaches itself, so this is production, and once it's detached, and its shape is completely formed by this integral, then this equation will tell you how it propagates. And we've seen what it does. It stays the same shape, goes with the speed of light. That means the whole problem is solved. Yes, in practice the integral might be hard, but it's a solved problem. In fact, let's write it down right now. H mu nu bar equals, there's some 4 pi dropping out and everything, gives you 4 pi integral source primed x minus x primed x d3x. There you go. Here's your general solution for gravitational waves if they are produced in a Minkowski spacetime.
Vivian, why did you change from T mu nu to T alpha beta in the integral?
I should not have done that.
Oh.
Otherwise, it would not have made
Oh,
sense.
right.
I'm sorry, it's constantly switching with alpha, beta to mu nu.
It's just that I thought it was a new
No,
indexing.
this is me being sloppy. Whatever alpha and beta is here should be over. In fact, that was question 2a from the midterm. Show which one of these makes sense and which don't. Now it makes sense.
When you have T alpha beta as a function of retarded time, does that mean just any time dependence in the tensor you would switch to TR, or does it mean that the T coordinate itself becomes TR?
No, every time dependence. Every time that you see a
So
T
just
as
the
an arc,
elements in
yes,
the tensor, not
yes.
the coordinates.
not the coordinates, no. No. So I'm not changing my alpha beta to alpha retarded and beta retarded. I'm changing the
Sure.
arguments. So
Okay.
if you want to know how the gravitational wave affects you now, you have to look at what the source did way back
Mm.
in time. How much back in time? Well, as much time as the gravitational wave needed to travel the distance between you and when it was produced. That's what TR means. So it's a solved system now, from beginning to end. Now that's nice, isn't it?
It's beautiful.
It really is. No, practice life is not that easy. Because
No.
rarely gravitational waves are being produced in the Minkowski spacetime. They're produced in Schwarzschilds and curved spacetime. So it means all of this does not hold. This is this is unfortunately only when the gravitational wave is produced in an environment that itself is hardly curved.
Is it because we assume that Xi is very small?
No, it's because we assume that the h mu nu is on top of Minkowski spacetime. So the gravitational wave is propagated, is
It's
produced.
because we say GMV is equal to the Minkowski MV plus
Yes,
h.
exactly. If you want to do it for more real life sources, you would have to replace the eta by, say, Schwarzschild. But it means many of the steps that we did, and we took a couple of Minkowskis inside derivatives and all that stuff doesn't hold anymore.
So it gets much more complicated.
Much more difficult, yes. Hence the thickness of this book. So this works at the moment that you're producing gravitational waves in a background that itself is not too curved. That would be here, for instance, if I just wiggle around two bowling balls.
So very small mass then.
The mass that curves the space-time. Yes, there's two mass sizes here in this problem. One of them is the mass that produces the space-time on which you calculate your gravitational wave. That determines whether you can use Minkowski or Schwarzschild or something else. That has to be small, otherwise it cannot have started with Minkowski space-time. Then there's a second mass scale, that is how big are the objects that are making the gravitational wave. Now that they also have to be small, because otherwise I cannot make the assumption that h mu nu is small compared to Minkowski.
Wait, but isn't also the mass that's creating the curvature also creating gravitational wave?
That depends on the situation. So if you have a stationary black hole, well actually that is a good example. If you have a stationary black hole structure, then you have this other mass floating around it, it will make a gravitational wave. Because you have two masses that are orbiting with respect to each other. Okay, but that means that the gravitational wave that is then being produced, unfortunately, finds its origin already in the Schwarzschild spacetime. So that means, unfortunately, you from the outset have to use a Schwarzschild. So all of this is only useful at the moment that gravitational waves are being produced.
So we have like two masses like in a Minkowski like orbiting around, then we
Yes.
can use it?
Yes, so if I take two bowling balls and I rotate them around each other and they're small enough, both of them, that they don't disturb Minkowski space-time that much. As in, they make gravitational waves, but otherwise do not make a huge dent in the Minkowski space-time, then this works. And yes, real-life situations are much harder.
But normally the dent that something would make in Minkowski spacetime is much more significant than the gravitational waves it would make. Right?
That depends on situations. There's two regimes in gravitational wave physics for rotating star systems. One is called the Emery regime. That means extreme mass ratio in spiral. That means that one of the two things that are orbiting is ridiculously much heavier than the other one. Why? Then because you can use the dent that the big one makes as the background space-time, and the resulting mutual gravitational waves is a perturbation, h mu on top of the bigger Schwarzschild.
Yes.
But if you have two masses that are of equal mass, so not an Emery is not an extreme mass ratio, but a singular value, or like an equal value mass ratio or something like that, then either both of them make the same amount of dent. So you cannot say one of the dents is more dominant than the other one, and we just take the gravitational wave as a perturbation on top of that dent. No, you have two dents now. And on top of that you have a gravitational wave.
In that case, couldn't you approximate it as one big mass with twice the mass of each thing?
Not really, because if you have two masses and each makes a separate dent, then you have a little bit of dentiness here, and you have a little bit of dentiness here. That's not the same as saying I'm going to take two masses and make one big dent.
But they're quite close together.
And if they're quite close together, then it becomes approximately more and more true. That is very true. But space-time curvature-wise, there really is a difference between one huge dent in one location and two
Yeah.
smaller dents with a
Yeah.
tangible distance between the two.
Definitely.
So there's two schools of gravitational waveform modeling, as this is called, finding the gravitational wave. And one of them is equal mass systems, and the other one is extreme mass ratios, where you just assume that one of them is much heavier than the other.
How often relatively do each of those occur?
The detectors that are now built and are sensitive to what we measure are the equal masses ones.
Okay.
So that means if there's an extreme mass ratio system out there, they might be. We even have some approximate waveforms for that, but we will not be able to pick them up experimentally. The machines are simply not built for those.
Okay.
So they might be there, it's just we don't have the machinery to measure them.
Yeah.
The wavelengths become are of a different scale. So, oh well,
Can I ask a question about the exam?
yes.
Yes,
Did you see Zev's email about
Yes.
wanting to do the 60-40 split versus the 100% exam?
Yes.
Do you think that will happen?
I know that it will not happen.
Okay.
And there's the shortest and most business-like answer is we're not allowed to by EPC rules.
Okay.
I've asked. I'm a member of EPC, but I asked the other members, and it simply is not allowed by the statutes of how we are supposed to grade our
makes
Of course.
sense.
So will we still be tested on 100% of the material or just the last 3 weeks?
No, I will focus on the last 3 weeks. So it's Schwarzschild, Robertson Walker, and this stuff, and of course some tensor formalism there.
Yeah.
But I hope you can imagine
Of
that the
course, you
first
still
2
need
weeks
to
you
know.
need to know that stuff because it's now part of your toolbox. But I'm not going to specifically explain to me one more time what we discussed in week 1. But I am going to assume that you know how a 4-vector works, for instance.
Yeah.
So the conceptual part is also going to be on the last 3 weeks.
Yes.
Okay.
Now, as you know, I take the RTTI approach for this.
Yes.
Explain to me how this and this works just in words. An application of something that you have seen, application of stuff that you know in a somewhat different context, and a completely new insight thing, of which you had the ingredients, but requires some out-of-the-box thinking.
Yeah.
Now, I think you've been supplied with everything that you need, unless you tell me otherwise.
It's a lot.
I know, but I think the part that I can supply you with, I think I have done. Right, you have the recordings of all the lectures.
Yeah.
You have the solution sets. I have the synopsis. Unless you can tell me here and now if there's anything in particular that you need outside of the answers to the exam.
No, thank you.
Okay. Well, I'm open to questions over email, of course. I will be traveling from tomorrow onwards, so I won't be tomorrow evening or so. Probably the first time I'm going to check my email. But then I'll be in a conference for a couple of days, so I'll be available, but maybe not as quick.
All right.
Okay. So there's that.
Thank you.
You're welcome. What I will try to do, but I cannot promise it, is by tonight, there's one exercise still that has to do with polarizations of the gravitation wave that I said you can do another coordinate transform to get the polarization out. Depending on how I'm in my time tonight, I might actually write that exercise out so you can just see how that happens. If not, do not be passive. The exercise guides you through it, okay? All right. So, good luck, all of you.
Thank you.
How are we on time? I have no idea. My bio clock doesn't work.
1-5.
105.
Okay.
Good time.
Okay.